Hey guys, welcome back to my YouTube channel. So last class we have detailed discuss about Fermi-Dirac distribution. So which is one of the very important thing that you guys will be. I think you guys learned it in a very good manner, like having heard before. So I hope let's continue that to the density of states. So density of states is nothing but the what it will state is the number of states present in the energy level. So states is the thing. That example, this is the lower part of EC, that is a conduction band, and this is the upper part of EB. So if we go over here, then the package of the energy levels will be tightly held. If we go down here also, the package will be tightly held. Like you see, the more number of energies here, but here there will be some distance. So if we plot the same over the energy levels, so just take this is the energy level E of E, and let's take this is the N of E. So N of E is nothing but density of states. So over the DE, so DE is some change in the distribution. So N of E, which is nothing but the density of states. So density of states. So let's take the lower part here and the upper part here as it is. So if we go over it, the presence of the density state will keep on increasing. If we go below this, the presence of electric state will be keep on increasing. So that's what we guys were mentioning like this way. Okay, I hope it is understood. So let's if what now our target is to compare the density of states and the Fermi-Dirac distribution. So that is what the thing that we are going to do here. So in the last class we have saw right the Fermi-Dirac distributive function. So let's tilt that graph. So last class we have that in the like the similar to that. So if we tilt that, how the thing will come? Let's see. So this is the distributive curve. Let's take it. So last class we have seen this is the energy level. So let's take this as f of e, and this is the energy level. Okay, so why we are doing is that in the density of states we have y-axis as the energy level. So for that only we are doing this. So if we plot it, so this is the value 1, this is 1 by 2, and this is 0. So if we plot it, then this is how it will work. The perfect graph will come exactly like this way, but nothing is ideal, right? So as the temperature increases, then that will be keep on this. So after this, it will trace like this way. Presence of electron will be 1. After that one, this is EF. So this is EF. Then here it will trace this way. So it is 0. So this is how we will be doing. Okay. So this is ideal for temperature T is equal to 0 Kelvin. So if the temperature increases, then the shift will slightly go this way. Okay. So lightly this way. So this is for temperature at T is equal to 300 Kelvin. So now we are going to take this 300 Kelvin into our ideal picture, and we are going to draw the distributive with the density of states. Okay, so let's take the case that we are going to compare the density of states and Fermi-Dirac distributive function. So I hope this will, after the diagram, you guys will be able to understand it very nicely. So let's stay tuned. So this is E of EV, then this is density of states, N of E dE. So first let's draw the density of states. So if we draw, this is EC and this is EV. Okay, so this will gradually increase. This will gradually decrease. So let's draw similar to that. It will gradually decrease. Okay, so let's multiply Fermi-Dirac distribution in this one. Okay, so if you multiply, what will happen? So let's take here this is a 1, this is 1.2, and this is something 0. So 1.2, let's make it a center. So this is 1.2 and this is 0. So let's take the 300 taken thing. So here this is EF. So this is center point. Let's take as a EF. So it will be slightly somewhere here, and then it will trace us to 1. So this is how the graph will look like. So this is for thing. But here this is electron holes. So if we multiply these two terms, the which two part will come into interaction is this one, this small area. Okay, so this one is our area of interest because we have multiplied density of states into Fermi-Dirac distribution. If we multiply both things, then this part only intersects. For this one, we have to find the thing, right? So this is f of e. So if we draw 1 minus f of e, then the graph will come like slightly like this way, just in reverse, right? So it will go like this way. So then that distribution will be this. So this is nothing but 1 minus f of e. So now we can able to clearly understand that these are the two parts will be intersecting if we multiply this one. So if we have to find the concentration, this is nothing but this is the free electron concentration. This is the free holes concentration. So that is what we are going to learn here. So how much amount of free electrons and holes will be present, comparing the density of states and probability of electron. So that is how the free electrons and free holes will be calculated. So this formula will be clearly depend on this integration because this is an area of intersection, right? So from the EC to infinity. So we may not know how much interaction will be. So EC to infinity, and this is density of state, and this is Fermi-Dirac distributive function over dE. So it's very simple, right? So this what we have obtained here is this. So if we have to find the free holes concentration, then minus infinity to EV over N of E, but the twist is 1 minus Fermi-Dirac distribution, which is the probability of presence of finding the holes. So everything we discuss, we have bring into together. So if we calculate this integration formula, we will be able to get the free electron and free holes concentration. So this obtaining the graph that the free holes and free electrons, this integration will be very tedious. So that we may not no need to worry about. We can directly use the end formula. So before that, let me draw another one thing. So how the free electron and free hole concentration will vary is this one. So this is N of E. So this is N of E into F of E d. Okay. So how much free electron concentration will be there is this much. How much free holes concentration will be there is this much. So this is P and this is N. So this much only will be there. So this is starting of EC and this is starting of EV. So this is nothing but E of EV and this is the distributive multiplication. So the N and P will be same if it is intrinsic. So if N and P, the amount, if the value is same, then we can call it as an intrinsic, right? If the N and P is varying like that, it's going like this and it's similar to that. So if N is greater than P, then that is N type. So this is how we can also sort the elements of distributor. So let's take another term. So P is same, sorry, N is same, but the P is different. So if N is less than P, then we call this as a P type. I hope it's understood for you guys. So I hope that you guys have listened to the Fermi-Dirac and distributive in the very good manner. So from the next lecture, let me write the what is the exact value of N and P, that I will return. Directly we can return. We no need to worry about the integration multiplication formula. That is not needed for any of your college examination or even for a competitive examination. So just you have to know what is free electron concentration and free holes concentration and how that is derived from Fermi-Dirac distribution and density of state. I hope this is very good understood for you guys. This graph is will be amazing for you guys to understand because we have combined both density of states and Fermi-Dirac distribution. From that we are getting free electron and free holes concentration. I hope this is understood for you guys. So even if you guys can't get it, please rewatch one more time. Then also if you can't get it, please ping in the comment section. For sure we will resolve your doubts. I hope this is understood for you guys. So please like, share and subscribe the channel. Stay tuned for the next lecture. So we are almost going to complete the semiconductor physics like this N type, P type, those things. After some 5 to 6 lectures, I think 5 more lectures are there. So once that is done, then we will be going to PN junction and then MOSFET, BJT and MOSCAP. So those things also we will be covering. So these all are very good foundation that is needed for you guys because in your later very core advanced subjects when comes, these kind of understanding will make you to learn and make you to understand very easily. So please don't skip the lectures, please watch it and then please go to the next lectures. So thank you, stay tuned for next lectures.